All right, well, I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. All right, so the basic thing we have to work with that we keep coming back to, right, is the residue theorem, right? What's residue theorem say? It says that the integral of f of z dz, around the boundary of some domain, it's equal to 2 pi I times the sum I equals 1 to, let's say, k of the residue of f of z zk, where z1, z2, zk are isolated singularities found in the interior of, well, just let's say found in D. I said D is a domain, so it's open. So anyway, there you go. That's the residue theorem. We keep using this pretty much everything we do. Let's make that J and J. Thank you. So I showed you like a rational integral last time. I'm going to show you another trick. And so this is a technique to calculate integral from 0 to 2 pi of various things, all right? So let me just run through some of the background here to start with, all right? So just as a setup, if we put z equals to e to the I theta, right, then that is equal to cosine theta plus I sine theta, right? And of course, z conjugate is e to the minus I theta, right? Which we could write as cosine theta minus I sine theta. All right? And you can solve these, right? We can take these and solve these for cosine theta. We get cosine theta wait a minute. Oh, well, z conjugate's this, right? But what else is it in this special context? Z conjugate's not always this, but for e to the I theta, what's this? This is also what? 1 over e to the I theta, right? Which is 1 over z in this particular context. So in this particular context, I have cosine theta. I mean, if you add these two equations, right, you get 2 cosine theta is equal to what? Z plus 1 over z, right? Because the sine thetas cancel. And if you subtract the equations, you get 2I sine theta is equal to z minus 1 over z, right? So let me collect my thoughts here. We've got cosine theta is equal to 1/2 z plus 1 over z. And we've got sine theta is 1 over 2I z minus 1 over z. All right. What's dz in this story? dz is I e to the I theta d theta, right? And let's see here, we could also write that as iz d theta, right? So in summary, what probably is, useful for us to just notice is d theta is dz over iz. All right? Okay. So it should be emphasized the formulas hold for the unit circle, right? Z equals all of these things I just wrote down, assume at the start. I mean, I could repackage everything I just did as, I mean, there's just one little proviso, you know, if, right? Z is equal to e to the I theta, then all this, all right? Okay? All right, so how does this help us do integration? You know? Well, let's look at an example. Suppose we're trying to integrate, I'm not sure, I guess I'll do it here. It's not going to be enough room. Rats, I'll do it over here. The integral from 0 to 2 pi of d theta over 5 plus 4 times the sine of theta. All right? Now, I guess, point of order, can you guys do that integral? As far as I know. I don't think I did another, yes, this is the other one. Sorry, I've been spending too much time around Soprano today. Let's see here. You know, gives me ideas. So how about this? We go backwards. Instead of starting with a complex integral and then finding a parameterization for the curve, plugging it in, we turn the tables. We start with an integral, a real integral, view it as the integral which comes from parameterizing the unit circle. See, I can look at this as the integral over the unit circle of what? I use the substitutions I just worked out, right? My d theta is dz over iz. That's my d theta, right? And then, well, 5 is 5. Okay. And then plus 4 times what? 1 over 2i z plus 1 over z. Yes. Oh, yes. Thank you. All right. Just gonna leave that like that. Won't bother anyone. Nothing to see there. Nothing unsettling about that expression, for sure. You happy? All right. I'm still missing one?
Yeah, you are still missing one.
Oh, yeah. Well, you know. There you go. Okay, anyway. Let's see here. So then we can multiply the z through, I suppose. And let's see here. So that's going to give us the integral over, I'm going to call this thing c, all right, of dz over, so this is c. All right, so I get 5 iz plus, let's see here, the i's cancel on the next thing, right? So I just get 2z times z minus 1 over z. There we go. Then I will clean it up a little bit more. So I've got dz over 2z squared plus 5iz, right, minus 2. All right. So far, so good? Can you factor that? Let's see here. Integral over c of dz. I bet it factors. 2z. I mean, I just looked at the notes, so I know it factors. But 2z and z is a good place to start, maybe. I need an I in the middle. I need a minus over. So if I do like a, how about like a plus 2i here and a plus I here, that should do it, right? Because that gives me an is and a 4 is, which is a 5 is, and it gives me 2z squared, and I got myself 2i squared, which is minus, yeah. So my question then is, where is the denominator 0? I heard a minus 2i, and also where else? Minus I over 2. These are the zeros of the denominator. So if I plot them over here in my picture, I've got one of my singularities right about here, and the other one at minus 2i, which is like down here-ish, right? So which one of these, so as we apply the residue theorem to this integral to calculate it, there's only one singularity inside the unit circle, right? So we just need 2 pi I times the residue of this function, this funny function here. 1 over 2z squared plus 5iz minus 2 at where? At minus I over 2, right? This is a simple pole, right? A simple pole in a complex plane. And in this one, we can use rule 4, right? We just use rule 4, differentiate the bottom, which gives me a 4z plus 5i, and I evaluate that thing at z equals to minus I over 2, right? Rule 4. And what do I got there? Got a 2 pi I divided by minus 2i plus 5i, I think. Because 4 times minus I over 2 is minus 2i, so that's a 3i. So the i's, they be canceling, and I get 2 pi over 3. Yeah?
Is there like a technique to factor the bottom? I mean, did you use completing the squares, like the 2z squared plus 5iz minus 2?
Oh, you're not content with my magical factoring?
Well, I just haven't got that point of factoring.
Yeah, sure. So, no, I did. 2z squared. Oh, the magic factoring I did was basically based on I looked at the notes and reminded myself that it factored nicely. So, and then once I know that, once I know there's a 2z and a z here, it kind of falls into place. But here's the method. 2z, I mean, yes, so I'll show you. 2z squared plus 5iz minus 2. So there's an algorithm. First of all, you factor the 2 out. All right, that's clear. Step number 1, factor out the leading coefficients. Step number 2, complete the square. All right, so we complete the square, and when we do that, we have to subtract 5i over 4 squared to be fair. There's still this minus 1 over here. That gives me 2 times z plus 5i over 4 squared. Now that gives me a plus 5/4. So I have a net of plus 1/4 here, I think. But tilt your head, squint, notice that this is actually minus 1 over 2i squared. Because 4 is, minus 2i quantity squared. And now it's the difference of squares. So all right. Now, oh, I did that wrong, though.
Yeah, so the 5i over 4.
I forgot the 5. So that's 25. I'm sorry, my bad. So that should be 25 over 4, right? 25 over 16, my bad, minus 1, which is 9 over 16. So I should have had, this should have been 3 over 4, 3 or 4i squared. Well, more to the point, I should have done, I could do 3i over 4. There's no need to put I don't need to put the I in the denominator or make things weird. So I think that's right. Then this is 3i. All right. Yeah, that's better. So then this becomes 2 times z plus 8 over 4 was 2i. And over here we've got z minus, rather plus, I over 2, right? Five fourths minus 3/4, 2/4, right? And then multiply the 2 over to here. Yeah. But yeah, I mean, that's a method. We can always factor any quadratic by completing this square. We just have to be more careful than I was in my first attempt.
Okay, yeah, I knew about the completing square, I just didn't know what the I in here.
I mean, yes and no. I mean, not really. It's just the arithmetic with I is, it is what it is, I suppose. All right, so let's do another one of these. I think I'll start over here. I don't like that board. Let's see here.
So to find the other scalarity thing in the circle, you just do negative 2i the residue.
Why would I do that?
I was just asking.
But the residue is not within the circle, so.
Oh, okay, I guess negative 2i.
Mm-hmm. Yeah, I mean, So, okay, so fine. Like, since we've done all this, example 2, not about the method, but about the method. Okay, so like, what if I was going to integrate over, say, I don't know, modulus of z plus 2i equals to 1. All right, and then dz over, 2z squared plus 5iz minus 2. I mean, we could do that. That would be a different problem, somewhat unrelated to my original trig integral, right? But given the algebra we just worked through, that integral is trivial to write down, right? Well, maybe trivial is too strong a claim, but this one, so you got to draw a picture, okay? I mean, like, that's so much of this is just draw a picture. So minus 2i, right, is the center of the circle. Its radius is 1, right? So it's like this. Now, the singularities of this are the center of the circle. Well, where else? Minus I over 2, right? Where's the top of that circle? It's at minus I, right? So if my picture's not quite right in terms of scale, but that point right there is minus I, right? Because minus I plus 2i is equal to 1. That's a point on the circle, the northernmost point. My point is simply that minus I over 2 is not within that circle. So the residue theorem says to calculate this, I just do 2 pi I times the residue of my function, 1 over 2z squared plus 5iz minus 2 at, in this case, minus 2i, right? What do you think that works out to?
Same thing.
Almost. Let's see how it goes. 2 pi I. If I differentiate this, I get 1 over 4z plus 5iz, all right? Evaluate that thing at z equals to minus 2i. Rule 4 again. And this time, the 4 term wins. See, so we get minus 8i. Wait a minute. Let me try it out. I'm sorry. Maybe, well, let me just work it out. 2 pi over minus 8i minus 10i, I think, right? Wait a minute.
Are you differentiating the same way you did before?
I was trying to.
So,
Oh, yeah. What's wrong with me? Thank you. So just that, right? I erased the z. I should just have 5i. Yes. Thank you. So minus 8i plus 5i, also known as minus 3, so we get minus 2 pi over 3. So close, but not quite. So if I call this function right here f of z, right? Example 3, I'll squeeze it right in here. All right. Suppose I want to integrate f of z dz over c 2, where c2 looks like this. And to be clear, this is minus I over 2, and this is minus 2i. What's the answer? The answer is 0. Because the one residue gives you a 2 pi over 3, and the other one gives you a minus 2 pi over 3. You get both, so you get 0. It has to happen. This is, I knew that was going to happen beforehand. Like, example 4. Suppose I'm integrating dz over p of z, all right? And c sub r. Well, I can tell you that this is equal to 0, provided that all zeros of CR, of P of Z fall within CR. That's not quite, that can't be quite true. Let me think about that some more. That can't be true. No, that's not what I mean. No, that's not true either. I'm going to erase it. Let me stop my mad speculation. There's a reason I knew this was going to be minus, but I can't remember what it is. Oh well. I'll find it for later. Let's see here. So good questions. Let's move on here. Next example. The next example here is perhaps a little bit more challenging because it's got a parameter in it. So let's work it out. So here we go. So example, what am I on? 5, okay. So this time we're trying to work out the integral from 0 to 2 pi of d theta over 1 minus 2p cosine theta plus p squared, where the absolute value of p is not equal to 1. All right, and here p is a complex number, possibly.
That is true. Not even exist anymore.
Oh, yeah. Example 4 was short-lived. Sorry if you didn't get it. But, okay, so we'll basically engage in the same trick, all right? So since we have integral from 0 to 2 pi, we can try to realize it as a complex integral. So let's look at it. We've got d theta over 1 minus 2p cos theta plus p squared. We make our substitutions. D theta is dz over iz. Then I get 1 over 1 minus p. The 2 we can absorb into the 2 cancels with a half, right? So p times z plus 1 over z, right, plus p squared. All right? And let's see here, what can we do with that? Got dz over, I'll leave the I out front. So when I multiply the z through, I'll not do everything at once. Sometimes I try to do everything at once and I regret it. So I'm just going to multiply the z through. It's tempting to multiply it all at once, but I'm just going to do one step at a time here. All right. Then that is equal to, what we got? dz I times minus pz squared plus, it looks like 1 plus p squared z, 1 plus p squared times z, and minus p. I think. So then, if we work this out, it factors, right? And so we can factor this as, I wonder where that came from. Oh, I see. So we can do z minus p apparently. I mean, if this is a factor, okay, so like, let me just take a step back here and tell you why that's a factor. That would be easy to learn. How could we learn that z minus p is a factor of what's above? Here's a simple trick. Plug z equals to p into here. If it's 0, the factor theorem says z minus p is a factor. What happens when we plug z equals to p in here? Well, we get minus p squared, right? Times what?
That one will be minus p cubed.
Yeah. Oh, that's good. This will be minus p cubed because this one also gives us a plus p cubed. And then we get plus p minus p. I was about to get really confused. Thank you, Shane. Anyway, it's 0. So that is indeed a factor. And once you know that, then, oh, okay. If I put a z here, and I had a z minus pz squared there, that forces me to put minus pz here in order to multiply, get back to that. And also, in order to get a minus p here, to get back to that minus p there, I must put a plus 1 here. And then you can check your work. When I multiply it out, I get p squared z, which is there, plus z, which is that, minus pz squared, which is this, and p times minus p, which is minus p. Now, of course, you could also go algorithmically through and do my completing the square thing, you know, like a robot, if you wanted to. I can't stop you. But, well, I mean, I guess I would stop you by, well, anyway, let's not make threats. So, see here, so I times z minus p times 1 minus, it just feels right to write it that way, you know? Great. So then what?
Consider cases, right?
Oh no. Then I'm What kind of cruel mischief is this? I go from page 154 to page 164. Oh man. I guess I'm on my own. And then we do what?
I would do cases.
You do cases? Oh, no. Well, maybe. Let's see here. So we have the integral from 0 to 2 pi of d theta over 1 minus 2p cos theta plus p squared is equal to the integral over, you know, the unit circle. And, oh, well, I just didn't need that one there. Ha. So, yeah, this. I think you can appreciate why the modulus of p rather, couldn't be equal to 1 in this example. If we're going to use this method at least, right? Like if the modulus of p was equal to 1, then we couldn't use this substitution reasonably. See, because if I have modulus of z equal to p, if modulus of p equal to 1, then that makes this 0 at some point, I believe. Okay, anyway, let's draw a picture. And I guess there are two pictures, aren't there? So we can either have modulus of p greater than 1, right? Or we can have modulus of p less than 1. And if I draw my unit circle, right? The zeros here are either what? We either up against z equals to p, or z equals to what? 1 over p. So these are our singularities, singular points. And all right, so if p is greater than 1, that means that p is out here somewhere, right? But 1 over p is in here. And flip the, the other story is true over here, right? If modulus of p is less than 1, then that means that p is in here, and 1 over p is out here somewhere, right? I'm not being careful about the direction of things. I mean, to be fussy, if p has angle, oh, fine. So if p has angle pi over 4, 1 over p has angle, it's like down here somewhere, right? So if like 1 over p is, so here's the origin. If I was to say 1 over p is out here, that would give it angle pi over 4, right? So then p would be at like minus pi over 4. Be fussy, right? So we are apparently interested in both residues, right? All right, so let's calculate those. What is the residue? Let me call this function right here, I guess I'll call the denominator g of z, right? So I'm interested in what's the residue of 1 over g of z at p, and what's the residue of 1 over g of z at 1 over p, right? And looks like, again, we can just use the rule 4, right? I don't know, maybe instead of using rule 4 for a change, I'm going to use rule 1. Okay, I'm going to use rule 1. Oh man, see, the problem with rule 1 is you got to have it factored properly. You know what I mean? So like, let me reformat g of z ever so slightly. G of z is minus ip times z minus p times z minus 1 over p. So I factored a minus p out. When I do that, that puts the z first, and if I factor out minus p, I have to divide the 1 by minus 1 over p, right? So when you multiply this back through, you get back to there. Now that I've done that, rule 1 is natural to use, right? So like, I'm gonna, fine, I'll even write the limit. Limit as z goes to p of, since when you multiply by z minus p, that drops out, you're just left with 1 over minus ip times z minus 1 over p. And this one, you got the limit as z goes to 1 over p. After we multiply by the z minus 1 over p, we're just left with 1 over minus ip times z minus p. All right? And then these limits just amount to evaluation, right? I mean, this is equal to like 1 over minus ip times p minus 1 over p And this one is 1 over minus IP times 1 over P minus P. Which is, I'll bring the I upstairs. Minus 1 over 1. When you bring I, it flips signs. When you move I from the denominator to the numerator, it flips the sign. You guys know that? Well, good. P squared minus 1. And this one, I over 1 minus P squared. Here's that phenomena again, Shane. If we were to encircle both singularities, funny, isn't it? Obviously, it doesn't happen for like if I just have one singular point, that won't happen, right? Because like if I have, for example, the integral of like dz over z minus 3I CR, well that's just 2 pi I, as long as, you know, as long as R is bigger than 3, if it's the, you know, this isn't even an example, this is just a comment.
So I guess, what's the difference between one of these and like an electron or something?
Oh, I don't know. I don't know, that's outside my, now you're outside my realm at the moment.
Oh no.
So, okay, so there are two cases. There are two cases, right? If the modulus of P is, so let's just write them down. I wonder, it'd be funny if both cases give the same answer, right? I don't think they do, though, do they? All right, so putting it all together, we'll assume the modulus of P is less than 1 for our first go at it. 0 to 2 pi d theta over 1 minus 2p cos theta plus p squared is equal to 2 pi I times the residue of 1 over g of z at where, in this case? P less than 1, yes, at P. And P is the one that's inside the unit circle. Very good. Which is, so we've got 2 pi I times I divided by P squared minus 1, which is 2 pi over 1 minus P squared. On the other hand, if the modulus of P is greater than 1, we get 2 pi I residue, the g of z I invented a minute ago, 1 over P, which is 2 pi I times I divided by 1 minus P squared, which is 2 pi over P squared minus 1. All right, moment of truth, let me check. So I got this example out of, I think, Vermeer, I said. And, you know, I think this is a good example. It's a little bit tough, but we can do it. Let's see here. Wheel. By the way, I still need to go back and fix example 10.24 on page 153. Something wrong there. What? Whoa, dude. Oh, my notes are lame. My notes just have one case. Oh, wait a minute. Oh, what was the deal? We had, if modulus of p is less than 1, 2 pi over what? Okay, cool. That's what I got on page 155. And if it's modulus p is greater than 1, we get 2. Hooray. There you go. So you want to get a little bit nuts? Check this out. What we got? So if I differentiate the denominator,
Are you using the same equation for the verb? 1 minus 2.
oh, thank you. Thank you. So if we differentiate the denominator, we get what, like a 2, my bad, we're differentiating with respect to p, right? So it's kind of dumb. It's just minus 2 cosine theta for the denominator, right? That's the derivative with respect to p plus what? 2p divided by 1 minus 2p cos theta plus p squared, right? That's just the chain rule for the reciprocal function, you know? But on the other hand, that's equal to what happens if we differentiate the other side. See, that should be equal to partial p of 2 pi over p squared minus 1 also. And if you differentiate that, we get what? We get 4 pi over, 4 pi p over p squared minus 1 squared. So if you want to make nearly impossible problems for students, you take the result you know, right, which was the example we did, differentiate it. Then you give them this. Yeah. That's some math contest nonsense right there, but anyway. Now, of course, this begs the question, how do you know that you can actually exchange the order of integration and partial differentiation with respect to the parameter? And the answer is, I don't know that for sure I can. I'm not sure that's actually possible here. It probably isn't possible for certain values of p, but it probably is possible for other values of b. We need what's called uniform continuity or convergence, something like, we need uniformness of the p dependence on the integrand, something like that. But it is probably true, at least for a lot of values of p, which is one of the values of doing examples which have a parameter. You can do things like this. All right, so let's move on. So the next order of business is integrands with branch points. All right, so let's see if I can do one of these monstrosities for you guys. Find a good example here. Well, I think I'm going to use the projector on this one because otherwise I think I'm going to end up hurrying at the end. So we'll just go slow with the projector. It's probably better. So obviously the technique that I've showed you so far today is of limited use, right? So like, unless you're doing an integral of from 0 to 2 pi of something, you're probably not going to use that one, right? But it illustrates an idea, which I think is useful. Also, I like these examples because they're a good place for us to gain further experience with how the residue theorem works, right? Like just the complex integrals we find ourselves doing, they're not that bad. This one we're about to look at, not quite as easy in terms of like the integral setup. Well, I don't know. This is kind of ingenious. There's something very ingenious about this, but this also. So here we're looking at the integral from, the idea is to calculate the integral from 0 to infinity of x to the power a divided by 1 plus x squared dx. So it's an improper integral, right? And we're assuming a is a real parameter, which is between -1 and 1, and it's non-zero, all right? So like I said, to capture this integral, we study f of z is z to the a over 1 plus z squared, right? That's going to restrict to this if we're on the positive real axis, right? So if we're going to do that, we need to use a branch that is holomorphic, right? We need f of z to be holomorphic on this Pac-Man, right? That forces us to use log sub 0 because that one has the badness right here, right? Log sub 0 jumps there. So if I define x to the, z, right here, z to the power a as that, let me erase some of this so I can write some of this stuff over here. So remember, z to the a, how do we define it? We defined it as exponential of a times really logs of alpha of z, right? You can choose whatever branch you want to define the complex power function, right? But this particular problem, you see, this particular problem has, in order to use this contour, right, in order to integrate some complex function around this contour, we want the complex function to be holomorphic, right, inside and on the contour. Yeah? So if that's going to happen, and we're dealing with, z to the a, we need to make this alpha. We need to make alpha equals to 0 because that makes the angle jump at 0, right? That makes the angle jump on the positive real axis, right? That's the first point. So that's why I use log sub 0 here as the formula for z to the power a, right? And then, of course, that just reduces to x to the a if we're on the positive x-axis, right? Okay, but more than that, notice that there's a difference between the L plus curve and the L minus, right? On L plus, we're a little bit above the positive x-axis, so our angle theta is 0, right? The angle is 0 on this one. But down here, we're approaching, the red line is the positive x-axis, okay? So down here, we're approaching it, so the angle, the argument along the L minus is 2 pi. Because L sub 0 takes angles that go from 0 to 2 pi. By construction, that's how that works. And then we let gamma r be the outside circle. Doo-doo-doo-doo-doo. Gamma sub epsilon is the small circle. Notice that the small circle goes clockwise, whereas the big circle goes counterclockwise. See how that goes? So we go clockwise, L plus like so. What? Oh, man. Dudes. Not cool. Well, that one is objectionable, like this, which is counterclockwise, right? So there's just one bad one here. This one. I just need to, like, scribble it out or something. It doesn't work. But, yeah, sorry about that. I'm sure this is the first semester I ever found that error. Sure there's no like video evidence of it being found in previous years and not fixed at this point. Rats. I really need to fix that. All right, anyway. So, like I said, gamma epsilon's the little circle inside. And so basically we're setting up this contour, right? Which maybe we should call like C sub r comma epsilon or something, because it involves both taking r larger and larger, but it also involves taking epsilon smaller and smaller, right? In both of those limits together, eventually the L plus and the L minus become essentially the improper integral over the real x, right? Because along here and here we have what? We have z equals to x, right? And down here you've also got z equals to x in the limit. Those are just the real positive axis. All right, so this particular function is a little bit easier than our previous example in terms of this one. Where's the singularity? Well, there's only one, and it's at z equals minus 1, right? So in terms of the integral over this closed contour, there's only one singularity inside, namely minus 1, right? And so I can calculate the residue there as such. It's a what? What kind of pole are we looking at here? Yeah, a double pole, right? So we use rule 2, or I don't know what. I think rule 2. Is it rule 2?
Yeah.
Yeah, it's rule 2. Rule 2. I'm having trouble with words today. Anyway, so we take the derivative. After we multiply this thing by 1 plus z squared, which knocks the 1 plus z squared out downstairs. That gives us a z to the a. To differentiating that gives us a z to the a minus 1, which you guys proved on the first test, right? Woohoo! Well, thought about it anyway. But and then maybe somebody did. Somebody did.
What was it?
Somebody did. Didn't I have this on the first test? Like prove the product rule, the power rule.
Oh, no,
I did that.
I think he did that.
Okay.
You got to choose.
Yeah.
Oh, you had a choice.